Looking at part B now, we've got a definite integral. This will be a good one. Definite integral from 0 to the square root of 3 over 2, t squared over 1 minus t squared, quantity to the 3 halves dt. So let's see, how are we going to begin? Well, the way to start these problems is to create a triangle and start to set up the 3 sides of the triangle with the Pythagorean theorem, and then from there get your trig functions to match up with what you need to sub for. In this one, you notice that at first glance, maybe there's not obviously a square root involved, which we need to set up the triangle. But if you look a little bit closer, there is a square root, right? When we see 1 minus t squared to the 3 halves, 1 minus t squared to the 1 half, of course, would be the square root. So I'm going to draw my triangle here. And thinking of, it's like we're thinking of it as 1 minus t squared. Oh, we're thinking of it as square root 1 minus t squared all to the third. Maybe that's a little bit easier to see it that way. Okay, so with square root 1 minus t squared, where should we position that on the triangle? Well, because it's subtraction, it needs to be on a leg. And my personal preference, I like to put it opposite the angle. So I put it here, 1 minus t squared, square root. So how can we fill in the other 2 legs? Well, the first part would have come from the hypotenuse, so the square root of 1, and the t would go here. So just kind of look at that again. Would this fit Pythagorean theorem? This squared plus this squared equals this squared. That squared plus this squared equals this squared. Yep, that works. Or you might think this squared minus this squared equals this squared. That's another way to think of it. Okay. So now using that triangle, we need to figure out what exactly we need to substitute and what trig functions will make that work. So we'll need, for our denominator, we'll need that square root, right? And again, we're going to combine it with the constant. So looking, hey, what trig function would combine this side and this side? Well, that's sine, right? So we've got the sine of theta equals simply, this was nice with the 1, right? Square root 1 minus t squared. So we're good to go there. We also need to substitute for the t on top. So what combines the t and the constant? Well, you see it right over here. Simple as cosine t, or the cosine of theta equals t over 1, so the cosine of theta equals t. Again, getting that t serves a dual purpose because we need to get a substitution for the dt as well. Don't forget about the dt. Well, we can get that pretty easily. So negative sine theta d theta will be the dt just based on taking those differentials. And hey, you know what? It looks like I went ahead and did the cube so I could see that happening already, that this will be the cube of sine. Okay, all right. Maybe not necessary, but we got there anyway. So we've got, let's see, what'll be cosine squared theta, sine cubed, and then negative sine theta d theta. There's our integral right here. Okay, I think I can probably get rid of this now. And it's that definite integral from 0 to root 3 over 2. I'm just going to keep these numbers, even though those are t values. I'm just going to keep them there and then worry about that at the very end. Some people might be saying, well, shouldn't we convert these to be values of theta? You certainly could. You could use cosine theta equals t and think of that as the t value and figure out the theta that goes with it and replace both of these with their corresponding theta values. My personal preference, and I think this goes for a lot of students in my experience too, we prefer to just leave them as they are, and then we'll convert everything back to t before plugging in anyway. All right, so here we go. Cosine squared over sine cubed times negative sine. Well, we're going to simplify, right? So we got the negative, one of the signs cancels. There's always going to be, shouldn't say always, but it's very, very common that you get some good cancellation when performing these problems. Okay, now this situation, cosine squared over sine squared with as an integral. Well, just looking at the guide, doesn't mention anything about dividing powers of sine and cosine. So what are we going to do here? Well, again, it's kind of like we're just in a situation that doesn't fit any of the kind of the go-to approaches, just kind of those general approaches. So we're going to have to start thinking and experimenting outside the box. Okay. What we want to do here, and the way to get to this answer actually very quickly, is just to think of cosine squared over sine squared as cotangent squared. And that might be something that some people do immediately or notice immediately. But then you're kind of stuck with, well, then what do we do with that? How do we take the antiderivative of cotangent squared? And the answer is to use its trig identity. So this problem really fits more in line with number 1. I believe it's number 1 of the secant tangent. It's kind of more in that vein. Or maybe it's even the first option under the other of secant and tangent that we're going to use this trig identity. Okay. So the trig identity is cotangent squared x plus 1 equals cosecant squared x. So, of course, we can subtract the 1 and do this. Now, how is this helpful, you might ask? Well, because we know the antiderivative for cosecant squared, right? It's negative cotangent. And, of course, we can do the 1 as well. So there we got the integral, at least up to this point, negative cotangent theta minus theta. Remember, this integral is with respect to theta, so antiderivative of 1 is theta at this point. And we're going to go from 0 to root 3 over 2, but these are t values, so we'll need to maybe distribute that negative since, looks like I do that on the next page. Let's go ahead and just distribute that negative. Okay, make them nice and positive. And then we got to convert our trig, our thetas, back into t. All right. Now let me explain what's going on here. So cotangent theta, we just need to look back at the triangle. And let me have that available here. Okay, so to convert cotangent theta, we'll look back at this. Well, if tangent theta is the root over t, then cotangent is t over the root. And that's what we have here, t over the root of 1 minus t squared. No problem. Now, then it occurs to us, but this is simply a theta. How are we going to go back to the triangle and figure out theta? I mean, cotangent or sine or tangent or whatever, secant. I can do that, but just the angle? Okay. So remember, we did say that cosine theta equals t. We'll just take the simplest of all of these. Well, then wouldn't theta equal arc cosine t, or you might say inverse cosine t? And that's what we've got to use. So if you just have the angle theta, well, go back and try and, there are multiple ways to do this, but try and pick the simplest one. So, if something like cosine theta equals t, I mean, Don't involve a square root or something if you don't have to. And then boom, we got it. It would all give you the same value in the end, and it would all be correct if you did it a different way, but why not go simple if you can? Okay, so now we have t's, t over square root 1 minus t squared, plus inverse cosine t going from 0 to root 3 over 2. And now we get to plug these numbers in. So I've done that here. Sorry, it gets a little bit small. Fractions within fractions and all that. Turns out this whole thing cleans up fairly well. Take a moment to write this out. I'll read it aloud. Root 3 over 2 over square root 1 minus root 3 over 2 squared plus inverse cosine root 3 over 2. Okay, all that minus. Now putting the 0 in, well, for this first part, just going to give us 0 plus inverse cosine of 0. Okay, now to clean it up. Looking here, well, squaring that would be 3 over 4. So I'm just going to go here for now. Root 3 over 2 over square root 1 minus 3/4. Inverse cosine root 3 over 2, well, that would be the angle pi over 6. Minus, still got the 0. Inverse cosine 0, pi over 2. For these, you can take the first value, because that would actually be the only answer for the inverse cosine function. Okay. And now this one you can go a bit further. Subtracting there, you get 1/4. And the square root of 1/4 is 1/2. That would cancel with this 1/2. And the answer comes out fairly nice. So we just have the root 3 in the end. And then pi over 6 minus pi over 2 is minus pi over 3. There it is. Okay. I've got one more example. I think we can fit it into this video. Okay. Let's see what happens in part C. It's the integral of x over the square root of x squared minus 6x plus 5. Okay, so looking at that, definitely something different going on. You know, I see that square root. I think every example we've done here has had the square root in the denominator. That won't always be the case as you look at more problems and homework and such. But it's probably more common than not with that square root to be in the denominator. Then we've got a power of x, just x to the first there in the numerator. Sometimes problems have other x's, sometimes they don't. So we've got just an x there on the top and then the dx. Okay, now what's different here is that we don't see these nice perfect squares inside the square root. And so we don't want to go to set up our right triangle immediately. We want to rethink that square root there because we need, you know, either the difference of two squares or the sum of two squares in order to begin to set up our right triangle. So what to do? Well, if you think back to your algebra days, there is a method of turning something like this into either the sum or the difference of two squares. And that is to complete the square. Usually that phrase sends shocks of fear into algebra students, sometimes calculus students as well. Let's complete the square. Not a task we're called to do all that often. How's this going to work? Well, what we're going to do is say, hey, look at that middle number. Take half of it and square. Maybe that sounds familiar. That's what we're going to add on. So we're going to think, okay, x squared minus 6x plus 5, because I see the 6, I need to think of that as x squared minus 6x plus 9. Okay, and this will have a nice square when we factor. But if I say plus 9 there, but really it's plus 5, then I need to subtract 4 to keep these in balance, right? So x squared minus 6x plus 9 minus 4, and then we factor, and there we go. Let's think of it as x minus 3 squared minus 4. There we've got the difference of squares. That'll work really well for us. Now, of course, the 4 doesn't necessarily have to be a perfect square. It did work out that way in this problem, but this could have been a 2 or a 3 or a 10. We would just think of the square root as the square root of that number, whatever it was. Okay, so rethinking this, replacing underneath, here's our integral now. Integral x over the square root of x minus 3 squared minus 4 dx. Okay. And at this point, we're ready to draw our triangle. Let me go ahead and slide this all the way up, give us some space. Okay. So we're going to begin with the square root. Now again, we see we've got subtraction there between, so it's got to be a leg. And my preference is to put it on this leg here. And then we'll fill in the other parts. Okay, well, if I see x minus 3 squared here in the first position, then that means it's x minus 3 that goes there on the hypotenuse. And if 4 is here in the second position, that means it's a 2 down on the other leg. So that this squared plus this squared would give me this squared. Okay. Takes a little practice to do these. I mean, it is Pythagorean theorem and all, but we probably never thought of the Pythagorean theorem quite this way, at least not very often. Okay, now let's set up our trig functions. So we need something for that square root. I like to begin with that one. Combine it with the constant, please. So that is a, what trig function would that be? Tangent. Tangent would be this over this. Okay, and then I'm going to multiply the 2 over at the same time. So 2 tangent theta equals our square root. Okay, we also need x. Okay, well, we'll go with the x minus 3, combine it with the 2. That's going to be cosine. Cosine theta will be 2 over x minus 3. So we can multiply this, divide the cosine. X minus 3 equals 2 secant theta, but if I want x, well, then I've got this last step of adding the 3 over, no problem. X equals 2 secant theta plus 3. And now this last one, again, serves a dual purpose. It sets us up to figure out the dx. Don't forget the dx. Taking the differential of both, dx, okay, and then derivative 2 secant theta tangent theta d theta right there. Okay, we're doing really, really good. Let's see how it unfolds. Plugging all those parts in, probably fit it. Well, that's okay. We've got the x here on top, divided by our radical, 2 tangent theta goes there, and then our dx, 2 secant theta tangent theta d theta. Okay, give you a moment to write that. Pause if you need to. Now we get some pretty nice cancellation, right? The 2 and the tan theta. And then I'm going to go ahead and distribute that remaining secant theta. Because, well, what else are you going to do with it? So we'll clean this up as much as we can. Leaving us with integral 2 secant squared theta plus 3 secant theta d theta. And now the question becomes, of course, are we going to be able to integrate that? Turns out we're going to get this one really quick. Now, we got it right there in the next line. Now it uses a little something that you might not be familiar with. If you took my Calc 1, this is not something that I make a point of in Calc 1. I don't think it's necessary or a good idea at that time. I think it's easier to just point it out when you get to Calc 2, and maybe uh, your Calc 1 experience, if you had another teacher, is similar, that they didn't point this out, and I'm talking about the antiderivative of secant theta. So let's start here with something we all do know. Secant squared, well, antiderivative would be tangent. So we got 2 tangent theta. The antiderivative of secant theta turns out to be this, the natural log of the absolute value of secant theta plus tangent theta. So there we go. Now, proving that this is the antiderivative is actually very simple. Just take the derivative of that natural log, and using the chain rule, you'll get some really nice cancellation, and you'll just get right back to secant theta. Okay. When we take Calc 2, it's kind of all of a sudden like, well, don't you know? You know, it's kind of just appears, right? And no, it wasn't in a prior section, and it was never pointed out even before right the moment that we need it. And yeah, you know, that's just the way it plays out here for this one. So it turns out, we know antiderivatives of sine and cosine, but tangent has a similar antiderivative, and then there's secant, cosecant, and cotangent. They all have antiderivatives involving natural logs, and those are all in the textbook, or well, that'd be easy to find on the internet. And so use those to your disposal, and you don't need any justification there. You see something like secant theta, boom, right there. Okay. And then just wrapping up, we need to refer at this moment back to our triangle and replace these trig functions with x's. Oh, yeah, so I've kind of got like, note, hey, keep that in mind. It'd be wise to look up the others as well, or at least know where they are if and when you need them for the other, all the rest. Okay, so here's our final answer. I've got 2 versions of the final answer. So, okay, so tangent, if you look back to the triangle, that was our radical over 2. So the 2's end up canceling, which is kind of nifty. Plus 3 natural log. Secant, looking back to that triangle, secant would have been x minus 3 over 2. And then tangent again is that radical over 2 plus c. Now I have another version of the answer, and very little changed, but I'll point out just why I decided to write this again. I simplified that completing the square piece. So I rewrote it back as x squared minus 6x plus 5. And the same thing here, x squared minus 6x plus 5. Why would I point this out as something of any significance? Certainly both answers are correct, and I'd consider both answers to be fully simplified even. So you'd have full points on a test or quiz on either of these. However, I want you to just consider for a moment putting your final answer back into the same style as the original question. So the original question did not have it in this form. It had it in this form. And so it's only polite to answer in the same form that you were asked. Think of it as maybe like a mathematical etiquette or a grace. Now, if they had posed the original question this way, then it might be better to answer in that same way. But since they posed the original question this way, there's kind of, you're going the extra mile to meet the preferences of the question asker by answering in the same way that it was put forth. Okay, well done. That is it for trig substitution. And of course, you're going to see many, many more varieties and difficult things in the homework. Maybe see some of you guys in our office hour time. Good luck to you.